Hello everyone, and welcome to the Microstructure, Metamorphics and Fluids session. First of all, I'm going to tell you about advances in microstructures over the last 50 years. Then Andy will tell you about how quartz analysis has evolved, and John will follow with the link of microstructures and metamorphism, and then Catherine will finish up by telling us about improvements in geochronology. So pre-PSG and pre-1970, most microstructural work was conducted by optical microscopy and the use of a U-stage. Electron microscopes were around, but only started to be used extensively for geology in the 60s. The microstructural sessions of the 70s were dominated by TEM, where images showing dislocations like the one on the right by Stan White were described as squiggly back lines on a grey background. Towards the end of the 70s, Twist published his quartz paleopixometer, which gave a method to measure the magnitude of paleostress from dynamically recrystallized grain size. Following this, many piezometers were developed for other minerals, some of which Ernie Rutter likely presented at past TSGs. In the 80s, methods used in metallurgy to study crystal structure started to be applied to rocks and minerals. Electron channeling gave us crystal orientations and misorientation images. An electron channeling map allowed all crystal orientations to be recognized, but this was a manual technique and took about 15 minutes per pattern. Also in the 80s, Rick Law spent much of his time staring at quartz Z-axes on a U-stage to define the mineral fabric, and Renée Heilbronner started to develop her models for shape analysis. According to Jeff Lloyd, EBSD snuck in through the back door in the 90s. It wasn't there, and then it was a major player, and most of the audience knew what it was. It was a far cry from the micro and strain analysis in the 70s. EBSD and pseudo-Kikuchi could easily be automated, and as soon as this was achieved, EBSD instantly claimed the preferred technique because of the pattern processing was effectively understood. Also in the 90s, several models were developed to simulate mineral fabrics by dislocation glide. Models for fabric formation improved from the Taylor-Bishop-Hill model of the 70s to the viscoplastic self-consistent modeling, or VPSC. And Rick Law was still looking down a U-stage and still does today. And meanwhile, Renée Heilbronner helped develop the computer-integrated polarization technique to determine quartz fabrics without the need for a U-stage. Also in the 90s, as computers increased in power, image analysis became an invaluable tool to easily characterize microfabrics. Further developments in the 2000s with EBSD detectors have made it more efficient to allow EBSD and EDS acquisition simultaneously. And the development of Channel 5 and Dave Mainprice's DOS programs have allowed easy processing of EBSD data. And seismic modeling using crystal structures have allowed us to simulate lower crust conditions to compare with real seismic data. And in the last decade, the recent development of high angular resolution EBSD, or HR EBSD, being applied to geology provides a rigorous quantitative measure of residual strain. And the MTEX toolbox has opened up texture analysis of EBSD data, and it is now more accessible than ever. We have also seen a development of grain-sized pixometers from the 70s, and this has now progressed to include subgrains, like these ones produced by Relais Goddard. And improvements to EBSD detectors have allowed progression from 1 point per grain and about 700 points overnight to mapping of whole thin sections at 1 micron step size in just a few hours. With these new techniques and the equipment, who knows what we'll be able to achieve beyond 2020. And now over to you, Andy, to tell us about quartz.
Thanks, Amicia. So I'm going to talk about how our understanding of quartz has changed over the last 50 years. So quartz accounts for about 12% of the continental crust. It's relatively easy to identify, but importantly, it's got some characteristic temperature and stress-dependent microstructures, which make it a user-friendly indicator of environmental conditions in the continental crust. Back to the 60s and 70s, early work looked at dislocations and slip systems in quartz from experimental perspectives. Multiple slip systems were recognized to control dislocations. The dislocation creep was recognized to lead to evolving microstructures in quartz. Quartz slip systems were recognized to have variable strengths, which importantly change under different temperature and stress conditions. And that these variable strengths in slip systems lead to the development of crystallographic preferred orientations. So this understanding of crystallographic preferred orientation development in quartz was taken further by important work by Gordon Lister in the 70s and 80s, who used Taylor-Bishop-Hill modeling of quartz fabrics to show how different fabrics may form under different stress and strain conditions. Importantly, this provided a set of different hypotheses to test against natural examples. And so in the 80s, much of the attention was refocused to natural settings, such as the Moyne thrust. We've already heard from Amicia about Rick Law's efforts on looking through U stage over countless hours. And importantly, this was probably the first time where proper focus has been given to how quartz fabrics vary over large regions and can change spatially and temporally with the evolution of structures such as the Moyne thrust. This was also the first time we were seeing figures such as those in the bottom right of the screen, where changes in quartz fabrics could actually be used to understand the development of crustal structures such as the Moyne thrust. Into the 90s and 2000s, our understanding of quartz developed further. Integration of a large number of experiments and natural observations led to recognition of three distinct dynamic recrystallization regimes, shown on the right, trending from bulging to subgrain rotation to grain boundary migration. Importantly, these different regimes were active over temperatures from 300 degrees up to and beyond 600 to 700 degrees, covering much of the ductile conditions in the continental crust. Additional work from John Krall recognized that not only do the microstructures change, but the crystal C-axis fabrics also change with temperature. Putting these two thermometers together allowed for another look at structures such as the Moyne thrust. Before the thermometry studies were produced, the quartz structures were used mainly to look at how strain and stress conditions changed over these structures. Now, with the new thermometers, it's possible to understand the thermal regime of these structures, paving way for a new understanding of the rheology of large-scale tectonic processes. Another important advancement during this time was further development of the recrystallized grain size piezometer. With relatively little effort, it's possible to measure recrystallized grain size quartz and determine the stress conditions under which they formed. If enough measurements are taken over a wide range of conditions, it's possible to then take these measurements to work out important parameters such as the strength of the continental crust. Now finally moving to the 2010s, 2020 and beyond, with all the advancement of knowledge that we've made since the 1970s and advancements in analytical techniques, many researchers are taking a new look at old data sets. With the rise of techniques such as electron backscatter diffraction, new automated analyses such as the EBSD grain size piezometer and high angular resolution EBSD, also the weighted Burgess vector, are allowing us to take large data sets and determine from those things such as geometrically necessary dislocations and measure grain sizes in a fraction of the time that would take us previously. Additionally, a significant amount of attention has been paid to the role of water in quartz. It's long been recognized that water affects the strength of quartz. However, it's not until the last 10 years where techniques such as synchrotron Fourier transform infrared spectroscopy, shown on the right, are actually showing where water sits within quartz. Additionally, modern experiments such as those done by Parsons et al. 2018 show that whilst water affects the initial strength of quartz, the volume of water can change during deformation. Other analyses such as that's Killian et al. 2016 are also showing us that our full understanding of the effect of water is not quite right. Whilst experiments show that dry quartz appears to be much stronger than wet quartz, in nature the conclusion is much less certain, with natural examples of dry quartz seeming to behave as weak as wet quartz. Finally, I'm showing you some very recent work from Tolk et al. And Tolk and Hirth, who've taken a look at old experimental data. On the left, you're seeing strain rate versus stress. These authors then started looking at how and show that there are two different stress exponents, n equals 4 and n equals 3. And on those, you can actually see a distinction between quartz CPO fabrics. So here we're seeing that really the CPO fabrics appear to be varying with stress and are less affected by temperature. So that's that's a very brief and incomplete understanding of how quartz has changed over the last 50 years. We've learned a lot, but what we've seen in the last 10 years is that a lot of what we thought we understood is becoming less clear. However, also with the advancement in techniques, it's probably likely that we're going to see a big change in our understanding of quartz over the next few years. And now moving on to John.
I'm just going to make 2 points really about what's happened over the last 50 years. It's obviously omitting a lot. And I think one of the themes that we tend to forget now, because the ideas are well established in geology, is what we gained by learning from metallurgy and learning about the ways that metals deformed and the ways that those deformation mechanisms left their fingerprints in the microstructure. That's not the whole story, but I think what I'd like to do is give an example here of that. So you can see that I've highlighted a phrase from a paper by Dave Elliott in 1973. He says, one point of this paper is to demonstrate that familiar pressure solution is equivalent to diffusion creep. Well, I hope that we all basically agree with that idea now, but these ideas were in the air at the time, but perhaps were not fully established. So let's see what he actually did to substantiate that. So these are line drawings and a photograph from his paper, and he's saying on the left there is a line drawing of a metal that's been deformed by diffusion creep, and the metal is dirty, it's got impurities, and these are fresh growths here. And what he's saying is on the right, he has got quartz grains, which have indented each other here, and which have got overgrowths of quartz there. So what he's saying is, if you read what he's written there at the bottom right, the reader is invited to compare the illustration of a metal deformed by diffusion creep with the photomicrographs of deformed metamorphic rock. So he was drawing attention to the parallel between what rocks do and what metals do in a productive way. And one of the payoffs from doing that is by comparing the microstructures, we can then say, well, all right, maybe the flow laws are the same. Now, all I'm doing here is showing perhaps some slightly clearer pictures, but they're just illustrating the same point there. So on the left-hand side is a material with impurities in the metal. These things that look like gaps aren't gaps, they're just clean alloy that has grown by precipitation during diffusion creep. And if we look at this famous picture on the right, we see we've got oolites, which were once spheres, and you can see that they've dissolved here and accumulated impurities there that are not soluble. And again, these areas here that are white are not gaps, they're where the calcite has precipitated. So the point is, it looks like the metal and the rock have done the same thing, and indeed they actually do. So what you can then do is say, well, all right, well, let's look at what the physicists and metallurgists have done in terms of deriving flow laws, and we can transfer those ideas to rocks. And these flow laws here, I won't go into detail, are basically the same, the ones that we use standardly in geology now, but they map onto the ones used in metallurgy. So I think there's a theme going through there, and it applies also, as the previous speakers have said, it applies to EBSD. It was kind of first applied to crystalline materials that were metals, and now we apply it to rocks. But I won't say anything more about EBSD, because the other thing I'm going to remark upon is rocks are more complicated than metals. They've got lots of minerals, they've got fluids, they've got feedbacks going on that metallurgists maybe don't think about so often. Look at this statement from Sorby, 1863. So it was Sorby that first addressed the idea of pressure solution in rocks long ago. And look at what he wrote there. He said, if mechanical force can be produced by chemical action, why should not the converse be true? So what he was alluding to there is something that I think is one of the key ideas from the last 50 years, which is the feedback between deformation and metamorphism. So mechanics and chemistry feed back on each other in lots of ways. So here's an example from the field. So here we have some granulite facies rocks in Norway, and you can see there in a different shade of green is a shear zone, high strain zone, and it's eclogite facies. So there's some kind of positive feedback going on there between deformation and metamorphism. We don't fully understand that even now, but one of the key things that's happened in the 80s is, and beyond, experiments illustrating this sort of thing. So here's Rutter and Brody dehydrating serpentinite, and it forms olivine, and the olivine is localized here along a little zone there which has had displacement on it. And so there's basically a link between the deformation and the extent of dehydration there. So that's a kind of key idea. We're getting this positive feedback. We need to understand it. We need theory and experiments to understand that more. It's kind of ongoing. And I've also put another one here where I think it's rather clear that the dehydration reaction here is localized in shear bands. So there's some kind of positive feedback. So what we've got in our toolbox now in the 2020s is the ability to collect vast quantities of data, both microstructural and chemical. So here we have just an example of such a paper. We've got the chemical analysis of some amphibole here, and we also have EBSD on that amphibole. This is showing misorientation there. And the point I'll finish on is that we now have this ability to collect vast amounts of data. It is still valuable to have hypotheses to be tested. Otherwise, we've got lots and lots of data and you're not sure what to do with it. But to be honest with you, I sometimes find, particularly with EBSD, that you're looking and seeing and yet you're having a poke around and you sometimes discover new things that way as well. So that is the end of what I have to say.
When it comes to understanding the deformation mechanisms that we've just heard about, we need to understand that timing really is everything. So how do we date deformation? Structures are dated using relative timing, cross-cutting events, uranium-lead dating of accessory phases, which are formed during semi-tectonic melts or formed during metamorphic reactions. Alternatively, we can date the fabric-forming minerals themselves. From endless deformational events to high-precision isotope geochemistry, we've come a long way in the last 50 years. And I want to start by emphasizing the importance of field relations for dating deformation events. Traditionally, structures were dated using cross-cutting relationships or, for instance, analyzing syntectonic pegmatites and bulk analyses of zircons, shown by this example from the much-loved Moyne thrust zone. We've also been able to study microstructures and relative timing, which has been fundamentally important for understanding major orogenic events key for the TSG community, such as the Grampian orogeny. There's a lovely example here from my undergraduate mapping area in Connemara. And then right up to date, this paper that's just about to come out in structural geology from Ian Alsop, who incidentally was my structural geology lecturer, continues to highlight the importance of descriptive field geology, relative timing and cross-cutting relationships for understanding major tectonic events. Over the last 50 years, scientific advancements have meant we can date minerals such as zircon and monazite with an ever-increasing precision. Throughout this, however, the key challenge is understanding those ages and linking them back to the field relations, the microstructures, and ultimately the events that cause them to form. 50 years ago, uranium-lead geochronology was done on bulk analyses of separated grains, losing that very important spatial context. Advances in situ techniques such as SIMS, laser ablation since the 80s and 90s have meant that we can now analyze minerals in thin section, maintaining that fundamentally important context. And petrochronology techniques combine microtextures, geochemistry, and ages to fully integrate the pressure, temperature, time deformation path of a rock. As time is short, I'm just going to focus on two dominant methods that we've used to date deformation over the last 50 years. Firstly, micas, which are dominant fabric-forming minerals, so if we can date them, this is an unambiguous way to directly link the timing to the deformation events, as highlighted by this early work from, again, the famous Moyne thrust zone by Simon Kelly. However, there's been a lot of problems with argon-argon, potassium-argon dating over the years, including problems with bulk analysis, understanding the closure temperature, inherited or excess argon, which have led to difficulties in interpreting ages. These challenges are far from solved, but developments in situ laser ablation techniques, as well as better understanding of the closure temperature and modelling, have meant that it's much easier to directly link ages with fabric forming events, as highlighted by this lovely in situ study from the Cyclades, and also this year from the Corsican Alps with this really detailed in situ laser ablation work. Moving forward, advancements in triple quad technology mean it's now possible to date micas in situ using rubidium strontium analyses, as well as combining with new techniques such as potassium calcium dating, which might circumnavigate some of the problems associated with argon dating. Uranium thorium lead dating of monazite is another way we've used to directly link metamorphism and deformation and try and explore that relationship that John just alluded to. And there were early studies done by Randy Parrish, which were largely bulk studies done by isotope dilution. So the bulk techniques, the problems with common lead have led to there being issues linking monazite ages directly to deformation events. However, again, advances in situ techniques, mapping, characterization of zoning, and using geochemistry of accessory phases to link to those metamorphic reactions and the deformation fabrics have meant that it's now possible to use these phases to quantify the timing and rates and conditions of movement in major orogenic shear zones. Moving forward, we can now use EBSD to look at the minerals we use as geological clocks themselves. So this is some EBSD data of monazite. And we can combine that with geochemical analysis, PT modeling, and even investigation down to the atom scale. All of this means that we're able to quantify the rates and timing of deformation at an unprecedented resolution. So in summary, we've come a long way in the last 50 years, from endless D-events and problems with bulk analysis to developments in high precision in situ methods, including SEM, laser ablation, EBSD. It's now possible for us to analyze fabrics, quartz temperatures, subgrain piezometers, and combining all of these techniques to link ages to deformation events, but keeping those fundamental field relations and hypotheses, as John pointed out, at the core of what we do. Our ability to measure smaller and smaller things with an ever-increasing precision is helping us to understand the way our Earth deforms and quantifying the mechanism and rates at which that deformation happens. And this will continue to be fundamentally important to structural geology as we move forward for the next 50 years. Happy
50th anniversary.
Great,